And we're live. So today we're talking about chapter 5 and coincidentally also lecture 5 of the YouTube material by Richard McElrath. So today we're looking, and I titled this Causal Inferences when I started watching the lecture in preparing. I think if I went back, I would probably title this Multiple Regression, but this is about identifying somewhat more of causal relationships instead of correlations, even though we're still looking at the world through correlations, if that makes sense. So when I read this and when I watched this, what came to mind for me, hey Anna, was that I now need to update all of my nerd joke material when I run stats classes because I can't say 42 is the answer to life, the universe, and everything. Now I've got to reference the Waffle House. So stepping into this, and it's been 2 days since I finished this presentation, and I haven't had the time to look at this, so it might be a bit stumbly. Hope you stick with me. When we get into this, the reason we do multiple regression, which is what we're talking about today, is all to do with spurious associations. So these might be hidden associations that we can't see because we're missing some important information. Or it might be that we want to identify causal relationships, but for that, we need sophisticated models that can take care of multiple variables at once, because otherwise we might be assigning association to a variable that's only an indirect path, more on that in a second, to the actual outcome. So the big thing here is that correlation is not causation. We've all heard of that one. I don't think we need to go into detail on this. The example the book and the lecture is running with is divorce rate and divorce rate predicted as either through marriage rate or median age at marriage, with the hypothesis being that the more people marry, the more people get divorced because more people can get divorced once they are actually married. And the other hypothesis being that older people make better decisions, big quotation marks on that one, better in this case meaning it leads to marriages that don't end in divorce. They might still end in very bad situations, and sometimes divorce might be the best way out of this, but that's going into sociology, and that's not what we're here for. So the way to assess these spurious association, would be multiple regression, which is mostly what we're talking about today. Then we could go into directed acyclic graphs or DAGs, and my heart started pounding when I read about this because this is what I'm here for. I really want to get into DAGs, and I hope there's going to be so much more of this in the next few chapters because I was not quite satisfied with how little there was in this chapter. That being said, the chapter was 40 pages long, and I can't fault McElrath for not going overboard. Other methods that he mentioned in passing that we haven't gotten around to yet are forks, pipes, colliders, and the backdoor criterion, but it seems as though we will get to this in the near future with the next few sessions. So this is where I go into the obligatory, from my end, DAG talk, and I'm trying to keep this short because I have got so much to say about this, mostly me telling you how much I love these methods. But a directed acyclic graph, you can unravel this starting from the end, jumping to the front, and then going back into the middle. So a graph is basically just a network. A network consists of edges and nodes. Nodes are entities in your study system. Edges are their relationships, how one is associated with the other or acts on the other. Directed, which is the beginning of this, just means that we have identifiable pathways. So when we have node A and B, for example, these are not associated with one another. They are interacting because we have one actor and one subject. Also, just because it's in the chat and it just popped up for everyone who can't see the chat afterwards, a book suggestion for directed acyclic graphs, The Book of Why by Judea Pearl. Thanks for that comment, Gregor. So that's where we go with directed in directed acyclic graphs. And then acyclic just means that we can't have loops. So that is both self loops and loops from one node to itself via multiple other nodes. So A on itself isn't viable, and A through B to C and then back to A, for example, also isn't viable. in an acyclic graph. So that just means that causality always flows in one direction, and there's no self-enforcement, for example. Now, in theory, those graph type analyses, especially the directed ones, can be combined to show direct effects and indirect effects. That's what I just mentioned here. So on the slide previously. So if we take this DAG on the right-hand side, A has a direct effect on D, but it also has an indirect effect on D, which is going through through M, not B, sorry. So in a DAG, and this is mostly always a hypothetical, which you can use to draw up hypotheses, directed edges depict causation. Now, you can elucidate a DAG from some model data or from some real-world data, using a model that is, but that doesn't necessarily mean that you've correctly identified these edges. So that's something that I'm currently working with on my PhD project, where I'm trying to identify DAGs from underlying data and finding methods that can correctly identify the right directions and magnitudes and even connections of edges is somewhat difficult. So this is, for most analyses, probably a very good tool to start off with to build hypotheses. Now, to resolve our issue of spurious associations, we mentioned that we would like to use multiple regression. So multiple regression has good sides and bad sides. The good one being that we can reveal spurious correlations and also uncover masked associations, which comes a bit later in my summary today. The bad also being that if you don't know what you're doing, which at this point, I don't feel super confident using this method yet myself, it can cause spurious correlations or associations, and it can hide real associations, which is exactly the opposite of the good. So it all comes down to, it depends whether this method is appropriate the way you're using it, or we are. Now, the aim of multiple regression, just as simple as possible with just two predictors, and it can have as many as we want. We want to answer the question of what is the value of one predictor once we know the value of the other predictor. So once I know the marriage rate, is there any more potential information to be gained in predicting divorce rate from now learning about the marriage rate, the age at marriage? In modeling language, this is just another linear model description that we have down here, where we specify our models the way we have in the last few sessions, and then we just add slope parameters for each individual variable that we want to have as a predictor. Now, just to drive this point home, with these multiple regressions, because we can introduce quite a lot of statistical effects which we don't want to see, we should always be mindful of which variables we use and how. Do we standardize them? Do we scale them? What do we do with them? But also maybe draw up those networks, even if it's just on a piece of paper, and then think about what could factor in how, because these really specified hypotheses may make it so much easier to run these multiple regressions in a way that you can identify what you actually are after, instead of having confounds bog you down. So again, I should have probably had this pop up earlier. The big question we're answering here is, how is each predictor related to the response once we know all the other predictors except this one predictor that we're currently looking at? That's the generalization from this two-factor or two-predictor example that I threw up earlier. Now, once we have settled on wanting to run a multiple regression, again, we need to define some priors. And going with this example here, again, for me, it became a bit clearer for why we standardize variables as often as we do following the Statistical Rethinking book. Because what we do here is, again, we standardize all of the variables, and that makes setting our priors somewhat easier when we are not quite sure of how the system acts. Because we can, for example, set the alpha parameter here, which is the intercept of divorce rate, which is now going to be the average divorce rate at the average marriage rate and the average age at marriage. And that just makes setting our prior to 0 so much easier, because this 0, now because it's standardized, means this is the mean value of the divorce rate. And thus setting this prior is so much more intuitive. Same here. McElraith mentioned in his lecture that slopes shouldn't be too strong. And for this, we would probably want to run a prior predictive simulation so that the priors don't get too intense when we have, I don't know, standard deviations greater than 0.5 in this example. So standardizing variables, just to drive this point home, can make finding priors intuitively much easier. And once we translate this into R, what we get is this quap with the A list therein, where we just have this kind of model. So this is actually not the model that I was showing just previously. I clipped the wrong one here. Because what this is doing, this is just a bivariate association between divorce rate and the age at marriage, and it should also have the marriage rate in here. I'm going to fix that and then re-upload it to our drive. So going into the prior simulation, again, the standardized stuff lets us interpret things a tiny bit differently when it comes to the prior predictive simulation. Because what we get here is that we have this Y space and the X space, and this is now expressed in magnitudes of standard deviation. So standard deviation of the raw data behind that parameter. And usually all of the data falls within ±2 standard deviations. So if we have slopes that predict outcomes far exceeding these points of -2 and -2 and then 2 and 2, for example, we should be very careful of what these priors actually mean for the model, because they are probably predicting relationships that are a bit too intense. So down here, you see how this prior predictive simulation would be done, where you just use the link function after having done extract prior, and you link your actual model onto the extracted prior as the posterior, which you want to predict for with the link function, and that's what you get as an output. So this is just using the model on its own priors to do your prior simulation, which is quite elegant, I think. Now, once we run this model, and here on the left-hand side, you can now see the correct model with BMM and BAA in there, we get this kind of an output here. So what does this output actually mean? What it means is that A, alpha, which is the intercept, following our priors and then plugging our models, our data into the model. Our alpha parameter, which is our expected mean divorce rate, is 0. Now, that doesn't mean no one gets divorced. That means it's exactly the mean of the data, because this is still standardized. Now, for marriage rates here, we have a slope of -0.07, but we have a super large standard deviation on it. And also this interval here is very, very broad. It came up in the lecture by McElraith that a lot of frequentist people always look at whether an interval covers 0 or not. That is not necessarily a criterion where you would like to then say, this is significant, this is not significant. It still tells you something about how much of the interval space lies on either side of 0. And in this case, it is definitely the majority of the interval space that lies on the negative side, coinciding with what the slope would tell us. I'm sorry, I have to close the blinds because I'm getting blinded from the side. And sun in Denmark, who would have thought? And with this kind of standard deviation that goes with it, and this very broad interval, even though it seems to be tending to the negative, this is not really a very consistent relationship. So marriage rate probably isn't the best predictor here. Even though when we regress it by itself, it doesn't do too badly. Now, the slope of marriage age is also negative, but very much stronger at -0.61 and an interval which is clearly in the negative. Now, this tells us that age of marriage drives the divorce rate with the Finally, standard deviation of the overall divorce rate being of a magnitude of around 0.79 standard deviations. So marriage rates, as a summary of this, is what we call a confound, because this by itself would make us believe that it would derive divorce rates. However, once we account for other variables, which are actually the drivers just through an indirect edge that passes through this node, going back to DAG speak, we can now elucidate the actual driver, which is age of marriage. So looking at this with a few different models, what's behind this is just that we have within each of these two bivariate models and one, would that be a trivariate, a tripartite? I don't know, just a multiple regression. So maybe the English speakers can help me out here in the chat, or maybe pipe up if you know the word for this. But basically what we see here, these are the estimates, and I hope you can see my cursor here. But in this picture, you can see the estimates of the parameters, so of the effect that a certain parameter has or variable has onto the outcome, which is divorce rate. And what you can see here is that as soon as we account for both variables in the model, the effect of marriage rate drops really far down and becomes much, much less certain for us. So if we look at marriage rate by itself driving divorce rate, what we get is a positive relationship, which intuitively makes sense because people need to get married for them to get divorced. However, maybe once we put them both together, this effect isn't as strong anymore, because maybe this effect here actually just hides the effect of young people marrying at a disproportionately large rate, for example, in certain states in the US. And that actually being the driver of marriage dissolvement after the fact. So then we can step into interpretation. And here again, we have our DAG. And this is just shamelessly copied from the lecture because it got late in the evening when I went through this. So once we know the median age of marriage, we really don't get a lot of additional information out of knowing the marriage rate. However, when we know the marriage rate, we still can get additional information by knowing the median age of marriage. So that is not to say that rate of marriage is useless, because even if we don't know our median age of marriage, it's still useful to know the marriage rate, because it can still help us predict divorce rate, even though we know in our hearts of hearts that really this is an indirect effect and we're kind of neglecting the real driver. So prediction, and this seems to crop up as a theme in this book and the lecture series, does not necessarily need a causal understanding. You can predict really well, even if your model is mechanistically completely off the mark. But if you then say you completely understand how the system works, you would be fooling yourself and or actively lying. Because most linear models, especially the ones of the normal kind, aren't very true to nature. So the ones relying on normal distributions. Now, we've got our results, we've interpreted it, but where do we go from here? So usually in frequentist statistics, we would do p-values, confidence intervals, what have you. But with Bayes, we always go back to the predictors. And in this lecture, we mostly looked at counterfactual plots, predictor residual plots, and then I think it was just posterior predictions. So I'm going to go through them step by step. The first one we're going to look at is just predictor residual plots. The purpose of this one is that we identify associations of predictors with the response while then controlling for other predictors. So keeping other predictors fixed, usually fixed at their median value. So in standardized terms, 0. Now, the recipe for this is to regress a predictor on other predictors, as you can see here, marriage rate regressed at age of marriage and the other way around. Then tallying up these residuals, which all happens in this first row of plots, and then regressing the outcome, which is our response variable, onto those residuals and seeing if we can find some form of correlation here. And what we can clearly see is that with marriage rate, we don't find much of a relationship once we fix age at marriage. However, once we have fixed our marriage rate and then we look at age at marriage, which again, keep in mind, these are residuals on a standardized scale. So that's why we get negative values here. For example, no one's marrying before they even conceived. We still get a relationship. So that's how we could use those predictor residual plots. Now, without having done too much beyond this point, what I think is this might be nice. This is probably one of those things you do to learn how these methods work. But as soon as we move probably beyond 3 or at maximum 4 predictor variables, this becomes infeasibly large a task to do and then to interpret. So I think this is really just there to tell us how the method works itself. And the important bit to take away here is to never analyze the residuals themselves, which quite often happens, and I've been guilty of that myself, where I just carried residuals from one model over to the next and then said, oh, I am now modeling my uncertainty, for example, which, yeah, at the time I didn't know better. Now I do. So the next one of these posterior checks, or not really checks, but posterior investigations of our model, let's call it, would be posterior prediction plots. So the purpose of this is to check for model fit and find model failures. And we've done these time and time again, so I'm going to go through them relatively quickly. The first thing we do is we draw samples from the posterior, then we analyze the plots therefrom and the intervals, and then question the output. So whether the output makes sense, whether we have outliers, which we can explain away, or whether that's something we need to go back to our statistical golem, our model, and then rebuild this to have it capture those outliers in a better shape or form. So on the right-hand side, you can see this kind of posterior prediction plot for our model with divorce rate and age in marriage and marriage rate. And what we can see are some quite big outliers here in Idaho and in Utah. Apparently that's because of some hardcore Christians who just don't get divorced once they're married. I'm sure Henry VIII would have something to say about that, but death rate wasn't in the model. So with this kind of plot here, we get our posterior mean and we get the interval, and we can see how much that overlaps with this dashed line here, which is the line that indicates that the prediction is exactly in line with the observations. So what we can see here is that in this yellow space, we have underpredicted the divorce rates, and in this space up here, which I haven't colored in, we would have overpredicted divorce rates. But overall, everything seems to cover this falling in line relatively well. So there seems to be good agreement of the model assumptions that we put in there, not that were enforced on us by some weird flowchart of normal distribution and what have you. Our assumptions that we baked into the model seem to agree with the data quite well. So we could be happy with this, especially because we can explain away these outliers. So again, the takeaway from this is to always use samples from the posterior rather than just summary statistics. Because if we would have just taken the mean or median and maybe the kurtosis of the posterior distribution of divorce rate, that wouldn't have told us nearly as much as if we had fully drawn out this kind of sample approach. Now, moving on to the last method that was covered in the lecture for posterior investigation, we can look at counterfactual plots. In these ones, the purpose is to explore model implications for our response. So what we do is we select one predictor at a time, and then we fix all of the other predictors. And this is what I meant earlier at the posterior predictive ones. I misspoke there. I was thinking about these, where we fix the predictors to usually their median value. So every other predictor except for the one we're investigating. So I think this is one of those methods that scales really badly with dimensionality as well. And then once we fix them, we compute the predictions for the response, so in this case, divorce rate, across the range of the predictor that we're investigating while keeping everything else fixed. And what you can see here on the right-hand side is exactly what we obtained from our persist table after we ran the model. A very strong negative relationship between median age at marriage and the divorce rate, and a slightly negative but highly uncertain relationship between marriage rate and divorce rate. So the takeaway from this is that this lets you analyze unobserved or impossible cases. And you have to be wary of when you fix certain variables or parameters in your counterfactual plots, that you don't go into impossible cases, because they might have some information for you, but you might also want to avoid looking at impossible cases because by definition, you'll never see them. So, for example, it wouldn't make sense to look at the divorce rate amongst, well, non-born babies, for example, and you could if you just fixed the age of marriage in a non-standardized form of age of marriage to -1, for example. The model could still do predictions at that point, but they would be completely useless. However, if you are like me currently, interested in species interactions from a wide array of data points, I can actually see this being somewhat useful because I can impute unobserved interactions, or at least I can try. If I trust them after the fact is a wholly different matter, but there's a good point to be made for looking at unobserved outcomes versus impossible outcomes. And I think that distinction didn't quite come across in either the book or the lecture as much as I would have wanted, but to me, it seems as though intuitively that should be quite a leap. Now, lastly, the book and lecture touched on mass associations, and don't worry, this is the last slide when I'm going to stop rambling and we can talk about exercises. The theory behind mass associations is that an association between predictor and response is masked by another predictor or by another set of predictors. I'm only always talking about this in the smallest cases possible because I don't want to redo all of the phrasing every time. So to then identify these masked responses, we require both predictors to identify the association of either, that is. And this is usually because these predictors are associated with the response in opposite directions, then cancel each other out and are associated with one another themselves. In addition to this, noise may also create masked associations, which would be called residual confounding, and then probably just comes down to you choosing correct priors, giving standard deviation and such to account for noise, or cleaning data, or if you can, and you're a field biologist or field researcher, try and get more accurate samples from the field. I realize I'm probably talking to a lot of people who get their data remote, myself included, and that's just not an option for us. So we have to find other ways of dealing with it. So when we look at this on the right-hand side, we can, in this case, a different data set, just see that once we account, so when we just run models by themselves, so these are bivariate models of this parameter against this and this against this outcome. So the outcome is shared between these y-axes, but the predictor is only shared in the columns instead of in the rows. What you can see is when we run bivariate models for this example here, the relationships aren't really all that strong, and you can see that they go in opposite directions. But once we include both of our predictors, so that are the two x-axes in these two columns, what we find is that we have quite identifiable, strongly opposed interactions with the actual outcome. And that's a literal textbook example of a masked association. And that is me with the summary of this chapter. If there are more inputs to this, just shoot. Otherwise, I would be transferring us to the practical exercises. All right, I guess I'm transferring us then. I just have to find the virtual desktop that I plopped my solutions onto. So quick show of hands, and you don't have to, like always, you don't have to be afraid to not raise your hand now. So who of us managed to get through the entire catalog of practical examples for this week? All right, that's the usual suspects, Gregor. Who of us managed to get through part of them? All right, cool. In that case, Anna and Suzanne, I would let the two of you ping pong off of each other for however far you made it. And then Gregor and I will just take over for the latter examples, if that's cool with you. Cool. Anna, do you want to start with the first? Well, let's. Okay. Sorry, I have to ask you two now. How far did you get, Anna?
I got through most of the easy ones and 2 of the medium ones. Yeah.
Cool. How about you, Susanna?
I even misunderstood. I only did like I run all the R code in the chapter. I didn't do the assignments even. So
right. All good. All good. Don't worry about it. In that case, Anna, how about you take the easy exercises and where you know Greg and I will step in, and then Greg and I will take over with you together for medium and hard.
Okay.
Good stuff. All right. Floor's yours.
Yeah. Do I need to share my screen for the first one? I only wrote down the answer. It's about identifying from a set of models which one is actually a multiple linear regression.
1 second. I'm just quickly
do you have them?
Yes, I have.
Okay.
I'm just quickly going to share my screen so it's in the recording. And there we go.
Perfect. Exactly. With those 4 models in there. And actually what I said is all of them except for the first one are actually multiple regressions, because you have not only X in there, but also Z.
Interesting. I actually am not, and I'm just seeing that I put a typo in here, because I only think that sorry, not 1 and 4. I've got a terrible typo in here. I meant 2 and 4, not 1 and 3. Okay. I only think that 2 and 4 are multiple regressions, because 3 is.
I mean, we can go through them. I mean, the second one is just that the intercept is missing, right?
Yeah.
But you have, exactly, 2 parameters. With the third one, you can also write it in a different way. It's alpha plus beta X and then beta Z. That's how I interpreted it.
Right, but that's still assigning the same slope to both. And isn't the heart of multiple regression that both of them can have a different slope?
I'm not sure, but I mean, what is Z then in that case? If it wouldn't be a multiple regression.
I think that's just regular linear model. What do you think, Gregor?
Later on in chapter 6, I think he uses one of this fixed slope models and calls it a multiple regression model. So I think it's fine because it uses 2 variables, so it should be a multiple regression. But of course, it makes no sense as we're fixing the slope, which, as you said, is against the purpose of the whole. But yeah, it's weird.
Yeah.
Could I just, if you could you equate xi minus zi to say yi, and then wouldn't it appear just like the first one?
That's what I was thinking too. Yeah.
Well, I did it in a different way, but yeah.
Well,
I don't know.
But I think this is just nice ambiguity about it.
True.
Yeah.
Okay, then we wait for chapter 6 for the solution.
We will.
I mean, the fourth is actually just a really normal one, which we always see as a multiple regression.
Yeah, I think we can all agree that 1 isn't a multiple regression here, and I desperately need to fix this typo here.
Okay.
So please, I have a question. So do we also agree that the number 2 is also a multiple linear regression?
Yes.
Because it's basically the same as number 4, but it's just that the intercept is missing.
Exactly. Okay. Thank you.
All right.
Okay. So then the second exercise is we should write down a model definition of the claim animal diversity is linearly related to latitude, but only after controlling for plant diversity. Okay, so you wrote it down in a different way than I did because I wrote it down in our code basically. But yeah.
Right. Do you have that to show?
Yeah.
Coolio. I'm stopping my screen share and giving that over to you.
Okay. Can you see it?
Not yet. There we go.
Okay. So for me, A is animal diversity, which I define here. Then we have latitude in here as L. We have plant diversity in here as well. So this is basically, I think, what is really important to write down. Oh no, this first part, yeah. Whoops. And the others are already model definitions, I think, which we did not really have to write down yet. But basically, yeah. A is somehow defined by L and P.
Yeah, beautiful.
Okay.
Completely agree with that one.
Perfect. The third one is actually similar. It's about writing down, what was it? Neither amount of funding nor size of laboratory is by itself a good predictor of time to PhD degree, but together these variables are both positively associated with time to degree. This time not really are, but written down. It's the same, just exchanging the variables. So you have the time for the PhD to finish is defined by funding and by lab size, basically. Yeah.
Mm-hmm.
Okay. So then I have a gap with E4, M1, and I can drop in at M2 again.
All right. Let me have a quick look at E4. I was struggling with E4 for a solid hour, and I'm not quite sure of my solution, to be honest.
Like a question remaining to E3. I'm wondering why like E2 and E3 are exactly the same question. There must be like a difference if the answer is exactly the same. I'm wondering if he might have missed the difference of the questions, or why would he ask like just exchange A and B with C and D?
I think the main difference between the questions comes down to write down the model definition, which is still the same part, and then indicate which side of zero each slope parameter should be on. I think
So
that's
the second part in the answer.
Yeah. Anna, do you have an answer to that?
I think what he wants you to learn is just when you have an idea in your head, how to write it down in code. And in E2 and E3, these, I mean, it's written down a different way, and still the model is the same.
Right, but which sign do you think the slopes of funding and size of laboratory would have in depicting or predicting time to degree?
Again, I don't understand that.
Okay, both funding and size of lab, as stated in the question, have taken together a positive effect on time to degree. What sign, so negative or positive, should both of those slopes have then? I think that's a bit of a trick question.
Would they both be positive?
Yes, that's the point. I would argue they. I would argue.
Yeah.
Sorry, I would argue they both have the same sign, so they are both either negative or positive. However, it comes down to how you interpret the whole. They have a positive impact on time to degree, because intuitively we would argue that, well, a positive impact on my time to degree would mean that time decreases. But if I'm just thinking about this in pure stats terms, I would understand this as the more funding I have and the bigger my lab is, the longer I take to do my degree, because there's a positive relationship. So I think that's the trick part of the question there.
Is the idea that trying to get at is that the correlation observed wouldn't be strong enough individually, but then that overall slope that you see when it's combined in the multiple regression is
I think that's
largely positive.
Yeah, Bernd, thank you so much for highlighting that we missed that difference there. All right, E4. Gregor, do you want to take a jab at this with me?
To be honest, this is the only question I just copied over from another blog because I was so confused.
Yeah.
Like, no way I could solve this one by myself.
So I'm just going to do the screen share, and I think then we can just talk about the different formulae in here. Because whoever wants to read this on either your website or mine, they can just go there. I felt as though I was slapping my brain against a brick wall for about a solid hour on this one. I even started up R, made up mock examples, and then tried to convert the different variables between each other to see if they came up with the same kind of posterior distribution. So if I could compute the posterior for beta C, for example, from a model that didn't contain beta C. So I tried for so long to somehow turn the outputs of model 1 into the outputs of model 3 that I was probably going blue in the face. And by the end, I did the exact same as Gregor. I just went to another blog, read through that, and yeah, that kind of makes sense. So what I ended up saying was that model 1, 3, 4, and 5 are inferentially equivalent because all of them miss one parameter, basically. This entire paragraph that I've written just boils down to they all miss one parameter, hence we can do the weird maths. How exactly to do that? I tried using R and I couldn't do it, and I didn't want to anymore. And I hope that inferential equivalency will become more of a topic in the next few chapters. What about you, Gregor? Same experience?
Absolutely. And I think I used a different blog to copy this over, but I get the same results. So we're on the safe side with this. But I feel like this is more like a math question than, and we haven't learned to answer that question yet. So I'm a bit surprised it's in the easy practices.
Likewise. Well, with a sample size of 2 blogs that you and me consulted, we still get a 100% rate of this being the answer. All right, medium exercises. Anna, do you want to take over again? Are you cool with that?
For the second one, yes.
For the second one, all right, cool. Then Gregor, you and me will just tackle M1. So the question is to invent your own example of a spurious correlation. An outcome variable should be correlated with both predictor variables, hence spurious correlation, because when both predictors are entered in the same model, the correlation between the outcome and one of the predictors mostly vanishes, or is at least greatly reduced. So I just went onto the book, so that's the PDF version that I uploaded to our cloud drive as well, and in that one on page 138, you find the exact code for it, which I just copied over, tweaked a few of the numbers a tiny bit, and then just put some different terms on it. So what I'm doing here is I'm just running a model in which I look at elevation, vegetation height, and air temperature. The spurious correlation being between air temperature and vegetation height. So when you run bivariate models, you would identify air temperature to be a driving force of vegetation height, and also elevation being a driving force of vegetation height. However, when you run the multiple regression, you really only find the effect between elevation and air temperature, and that is because there is an indirect effect, between elevation and vegetation height, because there's an indirect effect of elevation on vegetation height through air temperature, and a direct effect of elevation on vegetation height. So when I plot the raw data, that whole shebang looks like this. We can see that both of our predictors are correlated with one another, not so strongly correlated in their raw values with our response itself. Sorry, this right here is the response. So you can see that these are weakly correlated, but there's a relatively strong correlation in the raw data between my elevation and my vegetation height, which is exactly what I want to show. I put my model in here, which is just model specifications with a bit of touch up of different values in there. And then we look at what happens when we build our full model. And what we can see, so I didn't run a model for elevation on vegetation height. I just ran one model for air temperature and vegetation height, and then the full multiple regression, because that's the spurious correlation I wanted to show. And we can clearly see how the effect of air temperature not just decreases in magnitude, but even flips in sign when we just look at the mean, but with a big standard deviation and our interval being relatively big, we would not be certain of that kind of correlation. So concluding, we can then say we've got this indirect effect. And that was my example for it. Maybe, Gregor, you've got another more biologically relevant than my rather abiotic one.
I have turned my predictors and outcomes. So not really biologically relevant, but I just included a final plot with these coefficients at the end.
Right. I'm going to switch this over to you because I know that your visualization game is on point.
Thank you. Okay, let's see where we are. I'm sorry. Here we are. So basically the same steps. Simulating predictor 1. Predictor 2 is completely dependent on predictor 1. And the outcomes only dependent on predictor 1. Fitting 3 models. Model 1 is bivariate regression of predictor 1 on the outcome. Model 2 is a bivariate regression on the of predictor 2 on the outcome, and model 3 is a multivariate regression with predictor 1 and predictor 2. Putting this in a final plot, you can see that using a bivariate regression, we get a high or consistent relationship of predictor 1 and predictor 2. But if we add this or run this in a multivariate regression framework, we see that the relationship of predictor 2 vanishes, and the only thing we got left is the real relationship of predictor 2 to the outcome. That's it.
Fabulous. Yeah, no, that visualization really helps in here. All right, M2. Anna, back to you.
Quite funny because I basically have the same example for M2 as you have for M1, because except for exchanging plant height with plant species richness, I thought that
funny because that was my first thought to go with richness.
Because I thought like the one predictor elevation is going up while air temperature is going down. So that was my what I interpreted as being variables going both in opposite directions. So that's why I have your example basically for M2.
Cool. Do you have some visualizations which you would like to share?
Let me see. I can show you.
Because funny enough, my example for M2 also uses species richness, but I'm using location towards the equator and human footprint as the predictors.
Okay. I can share my screen if you want.
Gladly.
Right. Okay. Maybe this is interesting because it's kind of I try to kind of replicate the code from the book, except for taking my data. And as I interpret it is once we know about elevation, there's little value in adding temperature in explaining plant species numbers. I kind of also plotted A and sigma, why ever, I don't know. But I think this middle part is what is interesting, in those being on the same side while these being a bit off.
That's coef tab, right? The function to do this?
Yes. It's this
because
one.
I should really add this too, because this is just gorgeous. Yeah, exactly what comes out of my model as well, only with less of a visualization and different parameters, but we probably even did the same kind of simulation of data.
I think so, yeah.
Yeah.
Okay.
Gregor, what kind of variables did you choose for that one?
I was sticking to my very inventive naming scheme and called them outcome and predictor.
The theoretician, huh?
Yeah, totally. But I've included some DAGs in there as well. I can show them to maybe show the difference. So this is the DAG for the first question, for the first medium question.
Sorry, could you quickly flash the code that you wrote for this?
Yeah, of course. So that's using the ggDAG package, R package.
Ooh, is that really ggDad and not ggDAG?
It's ggDAG. I'm sorry.
Okay.
How
No, but
could you spot that so quick? Like amazing.
I've been listening to a Dungeons and Dragons podcast where the main characters are dads, and I think ever since then I've been a bit off. Cool. No, thank you so much. That looks like a great package. Cool.
Yeah, it makes some really cool visualizations, and it's easier to use than the Dagity package in some way.
Which great name, by the way, right?
Yeah, totally. I like that ggDAG is dagifying the Dagity package. So when you convert from the Dagity package to a ggplot, you use Dagify.
That's cool.
And so in the first question, there is no relationship of predictor 2 on the outcome. Using this stack, we can visualize this. And the outcome is only dependent on predictor 1. And in the second example, we basically have predictor 1 and predictor 2 influencing the outcome, and probably an unobserved variable that is influencing both predictor 1 and predictor 2, causing this mask relationship in the bivariate regression framework.
Cool. I definitely have to look into that package. That looks great. So far for networks, I've just been using iGraph, but this looks like it could show DAGs much better. Cool. Practice M3. And if we're going too fast, for the people who haven't seen these practicals before, just let us know and we'll go slower. Obligatory question to Anna. Did you get around to M3? All right, nope. So this is your cutoff point? Right. All right, Gregor, just you and me then. I'm going to read out the question. You're going to answer it. How about that?
Yeah.
Cool. So the question is, it is sometimes observed that the best predictor of fire risk is the presence of firefighters. States and localities with many firefighters also have more fires. Presumably, firefighters do not cause fires. Could probably get into a psychological evaluation here. Nevertheless, this is not a spurious correlation. Instead, fires cause firefighters. Consider the same reversal of causal inference in the context of the divorce and marriage data. So that's what I just talked in the summary. How might a high divorce rate cause a higher marriage rate? Can you think of a way to evaluate this relationship using multiple regression?
So I was keeping it simple. If there is more divorce, or after divorce, there are basically two new individuals who can remarry, which could then drive marriage rate. Because if there are more individuals, there's just a higher chance of marriage or remarriage, and then this could drive marriage rate. And in order to use this information in a model, we need to have a new parameter. I've called this, like there are various ways to track how this could influence the outcome, but I was using remarriage rate, hypothetically. So tracking how much of the divorced people get remarried, and then using this in a multiple regression rate compared to a bivariate regression rate, seeing if remarriage rate is really affecting the marriage rate itself. Because then we can basically uncover the relationship between divorce rate, or if this is all happening through the parameter remarriage rate.
Exactly what I've got to. Yeah. All right, I'm taking us over to the next question then, practice M4.
Shall I read it and you?
Yeah, let's go for that one.
Cool.
Switch it up.
In the divorce data, states with high numbers of Mormons, members of the Church of Jesus Christ of Latter-day Saints, LDS, have much lower divorce rates than the regression models expected. Find a list of LDS population by state and use those numbers as a predictor variable, predicting divorce rate using marriage rate, median age at marriage, and percent LDS population, possibly standardized. You may want to consider transformations of the raw percent LDS variable.
Cool. Yeah, so this just comes down to loading the data that was already used in the lecture as well as in the book chapter, which I'm doing right here, where I'm loading it, then duplicating it. Now I'm adding this percentage of Latter-day Saints members from values that have been obtained through Wikipedia, through one of the people who I like to consult for these blog posts, Jeffrey Girard, who really has fantastic blog posts on a lot of base stuff. I cannot recommend him enough, basically. That being said, I just copied over the data from there because I didn't feel like going on a hunt for a list like this. So having done this, I then had a look at the different distributions of this added variable. And of course, that is heavily zero inflated, just because there are a few states, Idaho and Utah in the US, who have a really high percentage of LDS members in comparison to the rest of the country. So because of that zero inflation, I wanted to put a log scaling on this so that I get a bit more of a even distribution in this. And then I'm also scaling this, so standardizing, Z transformation, whatever you want to call it, like this right there. I could have also used the scale function. I wrote it out because I wanted to be a bit more clear about how I'm doing it. But scale, in this case, $$ log LDS would have done the exact same thing. And just plotting this to show what the distributions look like afterwards. I build my actual model, which now multiple regression style includes 3 variables and 3 slopes to be estimated, plus my tiny intercept here. Setting relatively big standard deviations on this because there is quite a spread of percentage of Latter-day Saints. And then looking at the output, we can see that marriage rate is really not a very strong predictor here, and not one that we are certain of either. However, age at marriage and percentage of Latter-day Saints in the population of a certain state, both have very strong associations that are negatively driving divorce rate down as both of these parameters increase by themselves, and we're very certain of these. So once we know marriage age and percentage of Latter-day Saints, there is not that much to be gained from learning about the marriage rate as well. And that's my takeaway from this one. All right, shall I transition us into M5? Because there's not a whole...
sorry.
Oh yeah, no, Ollie, go for it.
Cool. I just wanted to bring up something. I was just thinking about Gregor's answer to M3. And sorry, I should have brought this up before, but I was still sort of processing it while we were going through that one.
Do you want us to flash it up again?
Well, no. It's just sort of it's quite a simple thing. But if you're looking for the causative effect of remarriages on marriage rate, I don't know whether is there some conflation between those variables already because of the way they're measured. So, for example, remarriage is a subset of the marriage data. So, your marriage rate includes marriages which are the first marriages people are having and also remarriages. So looking for a correlation between remarriage and marriage, are you looking for a correlation between two variables where one is the subset of another anyway?
Right.
Could that cause some issues potentially?
Absolutely, it could. And I think what Gregor meant when he was explaining it earlier, at least I'm relatively certain, and Gregor, you step in anytime. I think when you talked about marriage rate, you meant first marriage.
Yeah.
Okay.
Right.
But that's not necessarily necessarily what the data we've used so far has been looking at.
Absolutely, you're 100% correct in this. Really good to catch this. Yeah. So yeah, in the ideal world, what we would like to have would be first marriage rates and non-first marriage rates. Yeah, but well caught, really well caught, Ollie.
Yeah.
So, but in the end, like then, if we have first marriage rate and non-first marriage rate, they are not independent of each other, or like, because to be non-first marriage, you have to be married before, and that's why the non-first marriage rate gives you more information on being first married than actually just the rate of the second marriage, so to say, or?
Exactly that, Bernd. That's exactly why we have that spurious correlation, where one is a better predictor of divorce rate than the other, because they are associated with one another, but only one of them is the real driver.
Okay, so I got it.
Cool.
Nice.
Oh no, that's fantastic. That's what we're here for. I'm going to transition us over to M5, but please do like Ollie and Bernd here. And even if something clicks after the fact, or you want some more clarification on something we just talked about, but you feel as though you've missed your window, you haven't. This isn't parachute jumping. So practice M5. Because there's not much screen sharing to go on here, I'm just going to read it out and I'm going to give it over to you, Gregor. And then when we go into the hard exercises, I'm probably going to give that to you because your visualizations are just so much better. So I'm just going to give the screen share to you afterwards. So practice M5. One way to reason through multiple causation hypotheses is to imagine detailed mechanisms through which predictor variables may influence outcomes. For example, it is sometimes argued that the price of gasoline, the predictor variable, is positively associated with the lower obesity rates, the outcome variable. However, there are at least two important mechanisms by which the price of gas could reduce obesity. First, it could lead to less driving and therefore more exercise. Second, it could lead to less driving, which leads to less eating out, which leads to less consumption of huge restaurant meals. And at that point, I thought to myself, well, have you ever seen a TV dinner? That is unhealthy as hell. And can you outline one or multiple regressions that address these two mechanisms? Assume you can have any predicted data you need. How would you solve this, Gregor?
So I like the part where it says, assume you can have any data you need. But of course, we need to translate these mechanisms into parameters. And for the first mechanism, less driving leads to more exercising, more walking, basically. We could use the daily time spent walking as a parameter in minutes, for example. So we track the time each individual spends walking per day, and then we can regress this on the price of gas to see if there are any changes. For the second mechanism, that is less consumption of restaurant meals because you don't drive there anymore. It's basically the same. I would use a parameter which tells you how much food from restaurants you eat, which it's basically just a frequency measure. How much restaurant meals do you take per week or something, and then use this to regress against price of gasoline. Perfectly in a multiple regression framework.
Yeah, fantastic. It's exactly the same as I've written here. Just as you were talking about it, I thought it might also be interesting to maybe add the, I don't know, BMI of every individual to account for different, God, what's the English word for that one? For different speediness of digestion and what have you. base rate of calories burned per day, basically.
Metabolism.
Thank you. Yeah, metabolism rates. Yeah, it's the easy words, isn't it? All right, Gregor, you are free to share your screen for the hard exercises, because I don't think I've got good visualizations for those.
Yes, just need to find the hard questions. Here we go. All these, so just to highlight why I used here online, I have the print version of the book at home, and some of these hard practices online that you provided us access to are different than the exercises in the book. So I have hard practices online here, and at 5 I have these hard practices from the print book, just to make sure that we're on the same page. And all of these online hard practices use the same data, part of the rethinking package called Foxes. The urban fox, Vulpes, is a successful exploiter of human habitat, since urban foxes move in packs and defend territories. Data on habitat quality and population density is also included. The data frame has 5 columns. Group, the number of social group the individual fox belongs to. I think this is a factor variable, looking at the data. So not actual numeric values. Average food, the average amount of food available in the territory. The group size, the number of foxes in the social group. Area, size of the territory, and weight, the body weight of the individual fox. And the question 1, fit 2 bivariate Gaussian regressions using quadratic approximation. 1, body weight as a linear function of territory size, area, and 2, body weight as a linear function of group size. Plot the results of these regressions, displaying the maximum a posteriori regression line and the 95% interval of the mean. Is A, the variable, important for predicting fox body weight? So what I did, I loaded data and scaled or standardized all of the variables in the foxes data, but not group, because as I said, I guess group is just a dummy variable saying this fox belongs to group 1, but group 1 is not actually a numeric variable, which we should not scale. And then I fitted the model of body weight versus area. And as you have mentioned earlier, standardizing all of the parameters really makes selecting a prior on alpha and on the better estimates really easy. So I have used the same priors as you have used earlier as well. And then I just define a space, and I think we have done this quite a lot with with the link function, and applied basically the model to this sequence, to the space, and to get the posterior prediction. And this is the outcome of area versus weight. And we can see that there is a somewhat positive relationship, but it's absolutely not consistent. So the uncertainty around the slope is really high. You could instead just look at the coefficients of the output of presses as well, which would give you the same result. And I repeated the same steps for weight explained by group size. We can see here the relationship is way stronger. It's a negative relationship, and we are much more certain that this is a consistent relationship, that weight basically decreases with increasing group size. And that's my answer to it for now.
Great. Yeah, same here.
Cool. Should I just move on, or?
Yeah, how about it? I'm just going to chime in when I've got something significantly different. You seem to be on a roll. Keep going.
Perfect, thank you. Question 2 of the hard questions. Now fit a multiple linear regression with weight as the outcome and both area and group size as predictor variables. Plot the predictions of the model for each predictor holding the other predictor constant at its mean. What does this model say about the importance of each variable? Why do you get different results than you got in the exercise just above? So this is just the model. Again, prior selecting is really easy. As we scale the parameters, we include both variables, area and group size, and then this is another advantage of using set scores, C-scores, or standardizing the variables. We basically know that the mean of one of these variables is 0, which is the case, just checking that it's true. So I keep group size at 0 and then basically model the relationship between area and weight using link as above. In this case, just with group size equals 0. So we have to define a list with our sequence. So S is again the sequence we used in the examples above, and we set group size equals 0. Follow the same steps as above, and we can see that there is a positive relationship between area and weight, and this relationship is obviously consistent. So this is a big difference to the bivariate regression framework, and the same for keeping area at 0 while regressing group size on weight. So in this case, I set the sequence to group size from -2 to 2, and area equals 0 as an input to the link function. And here are the results. We can see that group size and weight are negatively related, and this is a really consistent relationship as well. And as we have seen in I think in medium questions, this is a perfect example of a mask relationship where area is positively related to weight and group size is negatively related, which cancel it out in a bivariate regression. But this is basically the good part of a multiple regression. It can uncover this relationship, showing the real, the reality, what is going on in this case.
Fantastic. I do have the exact same. I would just like to say I have, up to this point, so up until age 3, I've done everything with non-standardized variables, because, and that's solely for personal preference, because I come from an area where there are quite a few foxes. So I wanted to make use of a bit of intuitive knowledge of what foxes should be like, and I didn't want to do the back transformation to look at the actual parameter estimates. That being said, I get the exact same outputs as you, maybe not exactly a number because I couldn't do the back transformation here in my head, but the patterns are exactly the same, and when I wanted to keep something fixed, I just set it to the mean of the raw value.
Yeah, cool. Maybe just to add, this week there was a primer about Bayesian statistics in Nature, a paper published. I haven't read it completely yet, but what McElrath is always saying in his lectures is that we use informative priors, and you certainly had informative priors. Whereas this new paper gives really good examples and definition of what a good prior is. But I think, so this new paper certainly says that if you want to use flat priors, use flat priors or uninformative priors, whereas I would stick with McElrath that you always have some kind of knowledge, and that you should at least cover the realistic space with your priors, which I have done here. But your approach is even better because you have further knowledge and you implemented this knowledge in your regression, which is awesome.
Could you thank you so much for that input for that paper. Could you find a link to that?
I will, yeah.
Or if you have the PDF, if you could send me the PDF, then I can put that into our drive so that everyone gets access to it. Cool.
I will send it to you later on.
Fantastic.
I just want to ask, is it the paper from Nature?
Yeah, yeah,
Okay.
it is. It's a really good overview of all the methods in Bayesian regression, Bayesian statistics, not regression itself.
Cool.
Question 3. Now we take the average food variable into account for 2 more multiple regressions, body weight as an additive function of average food and group size, and 2 body weight as an additive function of all 3 variables, average food and group size and area. Compare the results of these models to the previous models you fit in the first 2 exercises. I just fitted a regression of average food and group size explaining weight. So you can see here parameters average food and group size, same priors as before. Calling this model 4. The same for all 3 parameters in one model, average food, group size, and area, calling this model 5. Writing my own function to tidy the output of the QAP, of the quadratic approximation, and then plotting it all. Model 1 is weight versus area. Model 2 is weight against group size. Model 3 incorporates 2 parameters, group size and area. Model 4, group size and food, average food. And now model 5 is basically using all parameters. And what we can see is that if we use average food in a multiple regression framework without area, we get a consistent relationship. The same for area without group size, without food. This is basically telling us, but we will get to this later on, I think. This is basically telling us that there is the same information incorporated in food and area. And that if we throw this in one model, the model does not know what it should do with the same information provided 2 times, and expresses its uncertainty in this case. So this is overfitting, and we can't be sure about the relationship from the posterior, from the model output. So what you should do with that is basically just sticking to one of these variables, either area or food. But I think, yeah, there's this extra question, is average food or area a better predictor of body weight? If you had to choose one or the other to include in a model, which would it be? Support your assessment with any tables or plots you choose. I've chosen no tables or plots, basically the one above. You can see that that food has a higher estimate throughout model 4 and 5 compared to area. So I would stick to food as we have more or stronger information implemented in here. So I would use average food instead of area.
Sorry, if I may jump in there.
Yeah, of course.
I've chosen the exact same. I also looked at the pairs of the underlying data, so the pairs plot, and you can see that both average food and area are quite strongly correlated with one another. So that if you have a bigger area, you also have, on average, more food and better food. You've done, yeah, see, there you go. Which explains that relationship quite well. I also looked at the outputs in number values. So I used some tables, came to the exact same conclusion. And from intuition, I think you made a really good point with saying, well, it comes down to the question we're asking. I went with the route of, well, I want to predict as well as possible from a causal standpoint when foxes get heavier or or less heavy. And I argued that average food is the much better predictor here to use, because that is undoubtedly the director effect than area. The fox doesn't grow big just because there's a large space. The fox grows big because that large space brings with it a large quantity of good food.
Yeah.
That was my reasoning behind it.
Absolutely. Yeah. Makes sense.
Back to you.
I mean, this is what we see in the model itself as well. That we have basically, even in a regression with all the parameters, we have stronger relationship between food and weight. And this is basically, the model is trying to simulate the direct causal path, or at least approximating it. But of course, we would have to test this with DAX, with directed acyclic class as well. And I think this was all of the online practices.
Yeah, there's just that one question which you already answered, but explicitly it says when both average food and area in the same model, the effects are reduced. Why is that? And we already went into it.
Exactly. This is
multicollinearity. Yeah. Ugly word, isn't it?
It is, yeah.
All right, cool. That pretty much brings us to the end of today. I know you've done the print questions as well, but on the off chance that I can't find a speaker for the next date when we will have a speaker, I would then probably just go to your website and pull those down and have those again as practice material, if you're cool with that.
Yeah, absolutely.
Cool, good stuff. If anyone is still up for it, and most importantly, Gregor, if you are up for it, we could have a look at the spline prior simulations from last time. But just quick show of hands, who's interested in doing that right now? All right, cool. In that case, let's go over to it.
I would be interested too, but I need to go have a different appointment. Have a nice weekend and see you next week again, guys.
Likewise. See you then. Thanks
Bye.
for coming.
So should I just share my website again and going back to chapter, it should be 4, right?
That's chapter 4, yeah.
Yeah, cool. So let's see.
I may even be able to help you find exactly which question it was on your end.
Probably from the hard practices.
Yeah.
It was the very last one.
It is 5.6 on yours. So 4H6.
Yeah.
There you go. That's the one.
Okay, so simulate the prior predictive distribution for the cherry blossom spline in the chapter. Adjust the prior on the weights and observe what happens. What do you think the prior on the weight is doing? So as you might have noticed, I'm using mostly the tidyverse, and I don't know if you're all familiar with the tidyverse.
Afraid not, no.
Yeah, it's using a more natural way of coding, I would say. So this kind of code.
Gregor, could I just ask a quick question? I noticed you used tidyverse for pretty much everything that you've done. Have you found that to be more helpful than going through basic functions?
Yeah, for one reason basically, or for two reasons. One, it's for me to understand something, I need to write it in my own words. And in this case, my own words are my own code. So this is certainly not the best way to write these algorithms. I think base R is just better in this case because the tidyverse is more verbose. It's more output, it's more to read. But for me, it's easier to understand and it makes it more tidier. That's yeah, the tidyverse. So for me, it's to learn from the examples McElrath provided. And the second reason is the rethinking package is built on Stan, the software Stan that is used for Bayesian regressions. And later on, for real analysis, if you want to implement this in your own research, you won't use the rethinking package. You want to use some real R implementation of STAN. And for this, there's this HRBMS package, which uses, which is basically an interface to STAN. And this is really helpful when you can use the HRBMS in a tidyverse framework. So this is one of the reasons that I want to use it later on for modeling.
Cool. Cheers.
Makes sense. Cool. So what I did in this case here, I was using a complete case analysis of the cherry blossom data. So using day of year and the year variable and excluding all NA values, so just using the complete cases, defining the number of knots, producing our knot lists that are equally spaced where we have a lot of data. We basically put a knot and then construct the basis functions using this BS function from the spline package. I don't know what the package is called again. So, and this is the linear model here using this this weird sign, which basically tells us to multiply each element of W with each corresponding row of B and then sum it up and add it to A by this plus sign. For this, I wrote this out as a function. So this tilde signs means the next part on the right-hand side is a function. The function is A plus the sum of the row of B times the W element. And what I did is I simulated how many parameters, what is N? I think 1,000 or 10,000 parameters for alpha, and the same for W, alpha with a mean of 100 and a standard deviation of 10. There we have N cal of B, so whatever, how many numbers we have in B. I simulated alpha and W for that. And then I applied this function to each row in B and to each element in W, which should be the same length, which is the case in here. So this map is just the tidyverse way of the lapply functions or sapply functions, or the apply families. And it's, I think, well, I don't think it is the case. It produces a nicer output, a more consistent output compared to the apply functions. And then we have mu. Mu is a list with 827 elements, one element for each year, for each observation in the data. And each element contains 19 estimates for the mean for each basis function, so which are 19 basis functions. We can then get the mean estimate by, again, applying the mean function to each element in mu, to each list in mu, returning a numeric output, a double. That's why I used map double here, which we then save to mu, overwriting the old input, and then plotting the whole. So this is one simulation for the prior predictive, for priors we used on W. So this is just one go. To see what the model really thinks, of course, we need to apply this many, many times. So this is basically what the model thinks with the priors we use on W without seeing any data. But this will be, of course, highly variable because is not based on any data, it's just based on W. And to iteratively do this, I just defined a function of I, where I do the steps explained above. I've put this in the function, and then I can call replicate here. You could use map as well if you want to. I replicated this approach and plotted it in a density visualization. So this is the whole prior predictive simulation density distribution, basically, which is not really it doesn't tell us much. Besides that, the model predicts that the day in year is around 100 with a normal distribution. This is just what we told the model. And now I define a function based on the priors on W. So on W mean and WSD, using our defined function above with the mu sampler, and then replicating this all and plotting it. And now I can, using this function prior weight, I can play around with my mean priors, with my priors on W, changing the mean and the standard deviation. For example, using a mean of 0 and a standard deviation of 20, we get this distribution, which is, let me just check it, just shows a wider spread in day and year. So while we get 18 and 120 here at the tails, we now get 50 and 150. So more uncertainty if we increase the standard deviation, which makes sense. If we increase the mean, we shift the whole thing to the right. Basically, that makes sense as well. And then I was trying to plot this on the real data. So this is, the model hasn't seen any real data yet, but it just shows me the mean when I apply the above defined steps, I think 1,000 or 10,000 times, and the spread for WD norm at 0 and 10. And what we can see here is basically what the model thinks for a mean of 0 and a standard deviation on W. If we now increase the standard deviation, we increase the uncertainty of our model again. If we increase the mean, we shift this whole part up. So what I actually think W is doing is, I think it's actually the real driving force of the prior of the models. So through W, we can actually express what we think day and year should be. So this is similar to our normal alpha and beta priors in a normal regression framework, because we pull this alpha and beta framework in our spline regression with our weight, with our W at each basis function. This is what really drives the model. That's what I think, but it was absolutely not clear in this case. It just shows that if we play with W, the whole prior posterior, the whole prior predictive simulation changes. So I think W is a really important factor here if we want to express what we think about the model. Does this make sense?
From a theory standpoint, it absolutely makes sense to me. I think it mostly comes down to me being wholly unfamiliar with tidyverse, which is why I had a bit of a problem understanding how it exactly does what it does. And I think the big solution to this is literally just me taking a tidyverse course at some point and getting over my snobbiness for making life hard.
Well, it's actually really fun to code in tidyverse. But the whole exercise, so what the whole code is doing is I write functions to play around with W to see what happens when I change W. And when I change W, I can see what the model thinks totally changes as well. So I attribute these changes to W, if that makes sense. Like, I really think that this is the case, that W is driving the model.
Yeah, no, I completely agree. Yeah. All right.
That was really pretty, Gregor. Thank you
Yeah.
so much. I admit, like, the per thing went over my head, but otherwise, I think the whole tidyverse thing looks really pretty.
Actually, so tidyverse is really, really easy, at least these deepler select, mutate stuff. And it's really helpful as well if you want to use SQLite as well. But I just started to use the pur function. So these map functions, these apply functions. And it's a total game changer. I started to use this 2 months ago. It was really, really hard. I was like, the only thing that is out there are 2 or 3 blog posts and the vignettes of the pur package. And it's a total game changer. Like, since then, I've not written a single for loop, and it's so much faster. It's amazing.
I guess we need a tidyverse study group after we're done with the base study group.
Oh my goodness, Gregor, I've just written this long, like 200 lines of code that's like all nested for loops. I'm going to do it.
Is that for your simulation study, Samuel?
Yes.
Yeah, been there.
So what I did for manuscript, I've had a script, an R script with the same as you, there's lots and lots of for loops, which ran for, I have to ask my wife, but I think night and a day on my laptop. I didn't have the desktop yet. And I just for me, like, the analysis is done and everything, but I just rewrote it with map functions, and it was like 2 hours and it finished. And instead of 2,000 lines of code, it was like 20. No joke at all. It's mind blowing. This is like, it's opening up opportunities. That's just crazy. I would really recommend to use them. If you want to read an introduction, just type in Google R for data science. And the first thing that pops up is the R for data science book, and just go through this book whenever you have 10 minutes of free time. Just read this book online and go through the analysis in there as well. Like, this is just the introduction to tidyverse and to the map families as well.
Thank you so much, Gregor. Yeah, I don't know if you realize how much time you may have saved me just by saying that. I'm very excited. I'm very excited. Thank you.
No worries.
All right. Cool, peeps. I guess we're at the end of our Bayes meeting today then. Thank you all for coming. I really feel as though we are getting a stride in at this point. I feel as though we know how we're functioning, and I really like the dynamic we're having. So I'm really looking forward to seeing all of you next week. And yeah, have a good weekend. Looking forward to next time.
Thank you so much.